Hi everyone, thanks for being in this session. So I saw that actually here we will speak, so the other speakers will speak quite a lot about many of the operational aspects of the future energy system. It can be buildings or specific types of renewable energy resources and how we can operate them or plan. What I'm going to speak about is something quite different because I will look at long-range national energy projections. And these are the kind of projections that actually influence especially important decisions when it comes to the energy transition. So maybe some of you might be familiar with this graph, which is the latest version of the Energy Perspectives 2050 for Switzerland. So these are the kinds of projections where, we are looking, let's say, into the electricity supply all the way from, we are here somewhere in 2020 for the next 30 years. So it's really a long range type of projection. And here, it's the example is of estimating the future electricity demand, but also the different how this demand could be supplied. And actually, it's very much these kinds of projections are used for, planning such decisions as how to implement the current Swiss vision of the net zero emissions by the year 2050. All Paris Agreement commitments and their monitoring, so monitoring of the nationally determined contributions, they also rely on these types of models and these types of projections, as well as investment decisions, let's say in the grid or in infrastructures like hydropower that last for more than half a decade and so on. So actually, if we would look at the common practice, how these projections are developed, how they are calculated, one of the most popular methods is the so-called technology-rich energy models. These are the kinds of models, so they're not statistical models, they're really mathematical models of we are looking at different energy resources and their extraction. It can be from solar energy to biomass or oil and gas. There are various transformation processes in the system, and then how energy arrives at its final consumers in the residential or industrial sector and anything like that. And in the most popular methods, actually so the algorithm within is that these models assume that the future transition can be represented by the system that has the minimum total system cost in the long term. And there are various arguments. One would say that, there's maybe we should look at assumed imaginary social planner that aims to to minimize costs for the society as a whole. And in that sense would plan the system accordingly. Also in economics, there are partial equilibrium arguments why these kinds of models are used. However, we also know there's really two big challenges with these types of approaches. And the first one, perhaps some of you have seen this graph. It's so here I'm using another example of the International Energy Agency. So that's the main international energy that both collects the global energy statistics, but also does future energy projections. And here, so they release the World Energy Outlook every year. These projections are every year. And here I'm just picking one example of the global capacity of new solar photovoltaic cells, so it's new installed capacity per year. And when the solar photovoltaic started growing, so here in black line you see the actual deployment of this technology, the projections of the International Energy Agency would also show that this rate of uptake of the technology would actually stay constant per year until 2030. So this is the years of the projections when they were published. But then solar photovoltaic, as we see around us, started accelerating very fast, and actually, ironically, still practically every year you see that, they pretty much thought that this is going to be the year when the growth is going to flatten out. And today's levels of growth are completely out of this graph. And I know I can already see many of you smiling, but these are actually the kinds of projections that are, extremely influential and used for many decisions. And one of the issues is here, and that we are trying to solve as well, is so we are working with these types of models as well. But we are using retrospective modeling, and here comes all the large data sets in order to improve the models. And one example is here. So here I just use a little bit older study of the example of United Kingdom and its electricity sector. So actually, if we would take such a model like the model before, and we would also say, we set it up from the year 1990, so pretending that, I'm, for example, living in the year 1990, and like today I'm still modeling for the next 25 years. So the projection that is produced by this type of model would show that in the UK at that time there would be coal and combined cycle gas turbines and nuclear power and some other technologies. So that's the model's projection. But then if we would compare it, because it's retrospective modeling, we can compare it with what has actually happened in the real world, and we see, because there's quite a big difference. And actually, interestingly, we also see that there's a range of underestimated technologies, especially like I just showed you with the example of solar photovoltaic in the case of International Energy Agency. So here, both many new technologies were underestimated, like wind power, both onshore and offshore, and solar power, but also this combined cycle gas turbines that were in the 90s also a new and innovative emerging technology. So there's actually what you a little bit see here is also that there's something that is not quite right in the models, that in this type of modeling, that introduces the systematic bias. And we were looking for what is the reason of the bias, and we found actually that since the typical models minimize the total system cost, but then if we look so this line shows now how the cumulative total system cost evolved through the years. And actually in the course of, so here it's 25 years, the real systems follow consistently a higher cost path than the least cost projection would show, meaning that there are, of course, in this messy world, many reasons why we are deviating from the least cost solution. And here one could also say, whether one could ask if this finding is also robust given the uncertainties in the data. So here we could run also, use Monte Carlo analysis to run a large number of scenarios where we consistently see that this deviation in cost from the cost optimal and the real world is never below, so here it's 13%, but it can be as high as 23%. So here, from the modeling perspective, then what we can do is, of course, we can then develop alternative methods that will then lead me to our next challenge. But one of the methods that we use is modeling to generate alternatives that allows us to systematically look not only at the model solutions that are at least cost, but can be, for example, here, can have up to 23% higher total system cost, so that we could encapsulate this real-world transition that we saw here in the UK. So, and this model allows us to select from a large, from this model, a large number of scenarios that are different from each other, but still not more expensive than this cap. And so if here it's again the same, this least cost scenario, and this is the real world transition, we could see that other scenarios that we would generate with this method could also have had lots of coal. Well, this has not happened in the UK, but there would be also scenarios that have lots of wind power. So here we can already say, okay, we would have anticipated with this method the future role of this technology. There's also scenarios with lots of, here in green, gas, CCGT, in orange, Again, we could say, we could anticipate the role of that technology. Here we have even more wind, and I could continue that, for exploring these scenarios further and further. But the challenge here that we get is also that when we allow this deviation of 23% from total system cost, we get, so here it's now 500 of such scenarios, we get very broad uncertainty. So we end up with these, instead of having one projection that was not maybe very accurate. For example, here in the case of coal, we would get anything from 20 gigawatt to 65 gigawatt of installed capacity, which is an enormous uncertainty. Then so we, at least in the sense, instead of having one least cost solution, we would be able to still encapsulate what was the actual transition, so here in these red points, but still, at the same time, we reveal very broad uncertainties that are difficult to work with. And this is the second challenge that we have in this field of long-range projections, that so even in our model, we already see these vast uncertainties. And now here, again, I'm coming back to this solar photovoltaic case, and here it's just, actually we did a systematic study where we compiled all projections that exist, both in academic literature, in the databases of the Intergovernmental Panel on Climate Change, but also in industry and so on. And actually, if you would see for solar photovoltaic generation in the from 2030 to 2050 projections, you would see that here we are getting basically anything from practically zero to this, something that is as high as practically the whole today's energy demand globally. And there are patterns, and some of these patterns are actually not even coming from different technology or cost assumptions, but from, for example, universities usually explore wider ranges, whereas industry and finance sectors tend to be more optimistic about global PV. Again, these optimization models that I showed you, they have quite broad range, but they tend to be rather pessimistic, as I showed with this example of International Energy Agency. So this is the next challenge: what to do? So on the one hand, we know how to improve these models, but then we end up with these very broad uncertainties, plus there are many models where we get into this enormous uncertainty range. So actually, and now where maybe my machine learning will come in. So our approach here is actually that we are taking a very untypical approach in the field, where we are trying to reduce uncertainties and improve the accuracy of these types of models. So we are, and this is a long-term project that we have. So we are, taking as one basis these the typical models, but also other kinds of models. We take all kinds of statistical tools, some of these machine learning toolboxes as well. Of course, large data sets, also interdisciplinary insights, so we collaborate with social sciences. And what we are doing is we are transforming Europe into a giant lab where we have 31 countries. And we are actually doing projections for all of these countries individually, including a very extensive retrospective testing, so we can, with the aim to really improve fundamentally this accuracy of the long-range national energy projections. And some of the very, very first steps that we have soon to finalize is just to show you. So, for example, here we created a large database of past statistics and country contacts of the energy systems in these 31 European countries. And it seems, when we think that national energy data and statistics is really available, but then if you are looking really at the kinds of data that we need for retrospective modeling from the year 1990, from, electricity load curves to investment costs for different countries, it really becomes an enormous exercise that we have invested lots of time in, and this data soon will be available publicly, openly. So if you are interested, do let me know, or do follow this, and then we will use it. And here we can use also this past data, what I just showed in this with the technology-rich models, for example, to retrospectively test them. And pressing something wrong. Okay, so here is just one example. I'll start from alphabet, with the alphabet. So we have Austria in Europe, and if we compare this least cost scenario, as I showed you before, with this typical model or the real world transition, you already, the values here are not so important. You just just by the colors, you already see that there's actually a quite some difference. What is really thought-provoking is, even in the UK, I showed you that this we found 16% deviation, so how the real-world costs were higher than the system costs in the cost optimal solution. Here we get even higher deviation. So it's actually, there was, which enormous, it means it will reveal enormous amounts of uncertainty for the future. But also if we look at other countries like Belgium and Greece and so on, you see the numbers are quite large. In some countries like France or Norway that are dominated by, large generation like nuclear or hydropower, we find a little bit lower deviations, but still with applying this kind of deviation for modeling future long-range projections, you would still have a very large uncertainty. So this is just one model, but we also can actually contrast that with other models. So we are building a socio-technical transition model, which is the kind of model that is inspired more from theories in transition sciences or in social sciences. There's also uncertainty forecasting models, which are the machine learning methods that look at past error of the models to forecast the future uncertainty. And actually, when we have all these three models, what really our novel contribution is that we have all that data that we can actually not only, basically use that data to calibrate, but we really do out of sample testing of these different models. So here we developed a comprehensive database of indicators. So here is just accuracy indicators to assess the electricity demand, for the example of Austria in the model. And here it's just the trend, so it's not even uncertainty, but we basically have it's like an accuracy test bench where you can see when models for what, when and how do they perform. And eventually our aim is to use those accuracy testing to actually know what types of models in which situations perform the best, so that we can eventually do these better long-range projections that do not anymore fall in the same traps of, consistently underestimated solar photovoltaic, as I showed you before, or enormously broad uncertainties that make the models basically not very informative. And actually, that's all that I had. So we are working on this. There's really a lot to be done. If any of you is also interested in it, do let us know. We are happy to collaborate. We are also hiring quite a lot for this project. So it's there's definitely, it's a huge challenge. It's a long-term project, and that we are working on. And that's it. Thanks so much.
Cool. Thanks a lot, Evelina, for your presentation. So now we're open for questions.
Hi. Whenever I hear about long-term forecasts, I also have a problem of validating those forecasts. How do you, do you have a good way of doing it? Because, when you make a forecast for the next 40 years, okay, maybe we will live till we find out, but many of us won't. So it's, how can you really work with such models? And, this is a research question. How can you do this? I'm also thinking about doing some long-term forecasts, but I always have this problem. So that's why I stick with day ahead.
Yeah, no, it's a great question. So maybe it was not entirely clear. So we use this retrospective modeling as a way to validate, which means it's not anymore only to validate we have many countries. So it's not so much, about validating by saying, in the 1990s my model had so much PV, and in reality there was, that much, and so on. So here we are really use that data for many countries for different model versions, and we are looking for a generalizable insight, right? Which types of models can, in the long term, better anticipate the structural change of the system? So it's not only about how to say, just knowing, the exact trend, the exact value, but really how the system evolves. And also for how to best estimate uncertainty, because there will be always around future projections uncertainties. So we need to ensure that we are able to quantify that as well as possible. So that's our approach. And then for the rest of the validation, it's one big, it's a huge field. So there's at least the state of the art is to use multiple methods. There's, I would say, 7 or 8 methods, from something called even stylized facts, for example, where the models reproduce the theoretical theories, how the system evolve. There's multimodal comparisons, so comparing different models as one of approach of validation. So there's really quite a lot of work going in that.
But can we trust those forecasts? I mean, okay, now look at the crisis in Ukraine. Who would have predicted, a few months ago, how the prices, the price of commodities, of energy commodities, or exchange rates would change? This is really unpredictable. And I mean, looking ahead 20, 40 years, so many things can happen that either we have extremely wide prediction intervals, and then the models are pretty much useless, or we are wrong. So, I mean, okay, I'm sorry I'm pessimistic, but I want to be convinced that long-term forecasts make sense, but I just don't see it at the moment.
So it's a great question. So I would say, yes, they do make sense, because one thing that we have, I mean, unless we are completely, in a world that that we can't probably imagine, the strength of these kinds of forecasts is still they are, we have hydropower. I mean, in 60 years in Switzerland, most of it is still there, unless we are really thinking about, Switzerland being wiped off the map, whatever the reason is, right? So there's lots of things that we are speaking really about long-term. We are speaking about technical constraints. We are speaking about resource constraints. I mean, we have as much solar irradiation as there is, right? We can model different levels of the technology efficiency, for example, or technology uptake. So there are really lots of robust things in these projections. Now, the rest is uncertainties, right? So something like what you said, and indeed, one of the things that we are looking at, or we will be looking at with these 31 countries, one can actually also sort out what are the quantities that we can predict, and I'm overdoing it. So we can project with uncertainties, and we cannot. And I would say for something even Europe-wide, if we are looking at hydropower, we can estimate it, even future growth of hydropower, quite well, because it's, first of all, it probably won't grow very much, but we pretty much know the sites and where it could still be built. But then if we are speaking about something like oil and gas price, which is very, very variable. So this is something indeed that, there are, groups that would forecast it also using machine learning methods in the long term. Ironically, you would not get such high uncertainty bounds as you would hope, because it's, we tend to think that oil and gas prices are very variable, and indeed they vary on short term, but actually the level is not as high as we typically imagine. So, for example, maybe for this one could say it's really there we need more, let's say, uncertainty methods allowing broad uncertainty bounds. But for other things we can project. And of course, the beauty still of these models is that we are trying to combine it all, right? So there's uncertainties and there's some things where we can actually say relatively well. And they're used, if we would not have those, exactly, but if we would not have those models, what else we would do, right, for the long-term planning? So we do the best that we can.
Great. Okay, further questions? So
Thank you. First of all, thank you for the talk, very interesting. My question is about forecasting versus scenarios, because if you don't have forecast, what else can you do? If I were a legislator now in the position to decide the energy policy of the next 30 years, forecasting is great, but I would rather be interested in the effect of my actions now in the next 30 years. So we know that energy policy is driven by political will, is driven by externalities we cannot control, but it's mainly driven by long-term planning. So how does this appear in your project? What approaches are you following? Thank you very much.
Yeah. It's a wonderful question. So, indeed, typically in the energy systems modeling community, we distinguish the kind of, projections of forecasting type of approaches versus scenarios. So more on, let's say, normative scenarios or what-if scenarios and the different decisions. But actually, they are not really exclusive, because if we have a scenario of what if now Switzerland has a carbon price, or what if Switzerland has a certain feed-in tariff, or what if Switzerland now really mitigates for net zero emissions. But then it comes already, we need to represent the system in a somewhat realistic way, right? And then again, this example of solar photovoltaic I showed, we still, after we have the scenarios, we need to be able to represent the rest of the system somehow adequately. And that's what we are trying to do. And then for the scenario methodology and for these, of course, these decisions, especially big policy decisions, but also, something like phasing out nuclear, implementing large policies, but also it can be, COVID or economic crisis or so on. So there are methods how they can be treated in this type of modeling as well. There's decision tree approaches. There's also ways to combine decision trees with probabilistic forecasting given. So that's something one of the paths we are trying out. And we have a huge historical database that I showed you, which allows us not only, to try things for the future, but really to see whether these methods and combinations of methods would have worked in the past on many countries.
Cool, thanks a lot. I think there was a question in the background.
Thanks. I have a sort of question in a similar vein. So, with this retrospective modeling, you see quite vast differences between what was forecasted and what actually happened in different countries. Can you correlate that or trace that back to specific public policies that happened that you didn't take into account?
Yeah, another great question. So, there's a limited amount of things we could do to trace that back. One thing that we already have the results, is some of that, so, there is typical policy, so whether, with or without support for renewables or something like that. So some of that indeed can be seen. So some deviations from the cost optimal solution come from the policies, but of course in the year 1990, we would have not known which policies will come when, and that's the same what we have today, right? If we are modeling until 2050, we don't know, is it possible that maybe one day somewhere there will be change in the policy on nuclear power? Just one example, and when exactly that would come. Another thing we are testing is also, for example, liberalization of markets. So we know, different countries have liberalized their markets at different times. It's really, in principle, it's a big game changer for the energy transition. The models, like they were in the 1990s or even 1980s, the same type of models are used today, meaning that we are kind of not, the system has undergone a principal change, but the modeling did not. And we actually can track back that some of the these deviations from cost optimality are also related to the fact that liberalization came, and actually with the more liberalized systems also these models are less fit, which is another interesting result. Our hypothesis was different, the opposite. So and for the rest, there can be really a lot done. So we have also, I said, if anyone is interested, we have so much data, and there's for sure a lot that can be done.
Great, thanks.
Thanks a lot. And just another question.
Thanks for the great talk. It seems in one of the first plots that some of the uncertainty came from very new technologies that didn't play a role in the 90s and then came up like wind and solar. How are you looking into new technologies that might come up within the next 30, 40 years, like nuclear fusion, tidal power, geothermal, which is now very low? How do you do that? Or what do you project there?
So there's two approaches. Basically, there's now a very big field I mean, it's very actually related to machine learning of these probabilistic forecasting methodologies that are primarily not even applied yet on the whole system, but on the individual new technologies. And actually there's quite lots of data that is available to already anticipate, because they are comparing many technologies from the past, but also from today. And there are drivers, the innovation does not come by itself. There are drivers, how much of research and development investment there was, what were the kinds of policies. And they can actually, feed all that into models, including the how the costs per unit of installed capacity go down. So this is currently very, 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 it's cutting edge, but it's getting extremely popular to do that. And so one of those approaches, the other approaches, of course, like here someone mentioned before, it's still a little bit of the scenario analysis, right? And then, and on the other hand, if we have something like geothermal in these types of models, of course, why these models are still good, why we cannot replace everything with only statistical models, is actually that in this technology-rich model, we can also take into account resource constraints, right? So both on the resources, but is there at all demand around that geothermal plant, whatever it's built to for heating? Is there a heat user close by? So in that sense, it's this is how. I stop here. I could continue, but.
Okay, thank you. I see it's an important topic.
So further questions? Oh, sorry, Esther.
Hi, thanks for the nice talk. I have maybe a bit a sidewise question. How do you incorporate industrial needs into your tests? Are they just part of the energy demand of each country?
Mm-hmm. And do you mean by industrial needs, you mean how much energy is consumed by industry?
Exactly.
Yeah. So it's, in the current model, so there are different ways, of course. In these technology-rich models, in principle, it's most of the time it's a bottom-up estimation, meaning that there will be, tons of steel produced and things like that, and then there's associated energy use and the potential efficiency improvements, and it's all summed up to the global level, and then there's to the national level, and then of course there's also the GDP growth and price elasticity. So depending how the demand might change depending on the prices and so on. So that's the typical approach in this. So in this project that I showed, we are actually focusing more on the technology, so supply technology. So we are a little modeling the industry sector at a more aggregated level. Mm-hmm. So therefore, it's more a combination of basically price elasticities. So depending on the electricity prices, will the electricity needs grow or go down? And
Thank you.